This idea of spin keeps popping up.
It does.
It's not like a spinning top, right?
Yeah.
But it's this intrinsic angular momentum.
Exactly. And what's really fascinating, and our sources today really dig into this, is just how many different spin values particles can have.
Mm-hmm.
We're going to take, a deep dive into particles with spins from 5/2 all the way down to 0.
Okay.
The mission, basically, is to get a handle on what defines them, what they do in the universe, and, the theories we use to describe them.
Right. We've got some great material here that really explores the characteristics, the roles, the theories. So let's maybe start at the top. Spin-Five-Halves.
Okay.
Now, these are fermions, which puts them in a specific box, doesn't it, based on the reading?
That's right. Fermions. So that means they follow Fermi-Dirac statistics. That governs how identical ones behave together. And crucially, they obey the Pauli exclusion principle.
Pauli exclusion. That's the no two particles in the same state rule, yeah.
Exactly that one. Keeps matter from collapsing, basically.
So for spin-five-halves, what does that mean for its, orientation possibilities?
Well, it means it has 6 possible spin projection states along any chosen axis.
6?
Yeah. Quantized values.
Yeah.
Minus 5/2, minus 3/2, minus 1/2, then plus 1/2, plus 3/2, and plus 5/2. All in units of sig, the reduced Planck constant.
Wow, okay.
And having that many options, well, it makes them inherently more complex to model than, say, your everyday spin 1/2 particles. Some of our sources really stress that complexity.
6 ways to point itself. That definitely sounds more complicated. So what kind of theories do we even use to tackle these?
Yeah, the theoretical toolkit needs to be more advanced. You can sort of generalize the Rarita-Schwinger framework, which we'll touch on later maybe. But the real headache, and several articles pointed this out, is trying to build consistent interacting theories for elementary particles with spin higher than 2.
Interacting theories.
Yeah, how they affect each other. You can run into big problems, like violating unitarity.
Unitarity, the probability thing. Everything has to add up to 1.
Precisely. Or you might break causality effects happening before causes, or the theory might become non-renormalizable, meaning you can't get sensible predictions out of it.
So just the idea of a fundamental spin-five-halves particle is like pushing the limits of our theories. Have we actually seen any elementary ones?
Good question. No, as far as we know, there are no elementary spin-5/2 particles.
Okay.
But, and this is where our sources get interesting, composite baryons can exist in excited states with spin-5/2.
Composite baryons made of quarks, right?
Exactly. 3 quarks. The total spin comes from a mix of the quark's own spins, and now they're orbiting each other inside the baryon.
Okay, so not fundamental, but super energized versions of more familiar particles. Any examples mentioned?
Sure. Some of the heavier delta resonances, excited delta baryons, they show up with spin-5/2.
Delta.
And also some nucleon resonances, the N-star particles, excited protons and neutrons, potentially other exotic baryons too.
Mm-hmm.
But, and this is important, the sources always emphasize these are incredibly short-lived. They decay almost instantly.
Right, fleeting glimpses. So fleeting and hard to describe theoretically, why bother? What's the big deal about studying them or even thinking about the hypothetical elementary ones?
Well, 2 main reasons, really. First, if we did find an elementary spin-5/2 particle, that would be huge. It would break the standard model, likely point towards new physics.
Like what?
Maybe something like supersymmetry or string theory. Some models mentioned in our readings suggest those frameworks might handle high spins better.
Okay. And the second reason?
Studying the composite ones, even though they're short-lived, tells us a lot about the strong force quantum chromodynamics, or QCD. And it helps refine hadron spectroscopy, which is basically how we map out and classify all these composite particles.
Got it. Okay. Fascinating stuff. Let's step down a notch to spin 2. These are bosons, right? A different beast entirely.
Totally different. Bosons, which means they follow Bose-Einstein statistics. Multiple identical ones can occupy the same quantum state, unlike fermions.
Right, the opposite of Pauli exclusion, so they can pile up.
Exactly. Leads to very different collective behavior.
And how many spin states for spin 2? Not 6, I assume.
No, 5 this time. -2, -1, 0, +1, and +2.
5 states. Bosons. What theories describe them, according to the sources?
Well, it really depends if they have mass or not. For a massless spin 2 field, the theory is incredibly constrained. It actually ends up being equivalent to linearized general relativity.
Einstein's gravity.
Wow. Yeah, in the weak field limit. The field is symmetric and traceless, reflecting how it interacts with space-time geometry.
And if it's massive?
If it's massive, there's the Pauli theory for free propagation. But interactions get tricky again. Our sources mention this thing called the Van Dam-Veltman-Zakharov discontinuity.
That sounds complicated.
It is. It basically means a simple massive spin-2 theory doesn't smoothly become the massless gravity theory as you'd expect. People are working on theories of massive gravity to try and sort this out.
A very subtle theoretical puzzle. Okay, so what are the actual examples? Spin-2 particles we know, or think we know.
The big one, the poster child, is the hypothetical graviton, the quantum of gravity.
Right, mediating the gravitational force.
Exactly. Predicted to be massless, because gravity has infinite range. And its spin-2 nature comes directly from gravity coupling to the stress-energy tensor, which is a rank 2 object.
Detecting it directly seems impossible, though.
Immensely challenging, yes. But gravitational waves, ripples in space-time, those are basically coherent floods of gravitons. Observing them gives us really strong indirect evidence.
Okay. Indirect evidence is still evidence. Any others?
Yes, composite ones again. Tensor mesons. These are quark-antiquark pairs with a total spin of 2. Examples like the F2-1270 or the A2-1320 meson pop up in the literature. Studying them helps us understand QCD, the strong force.
So, the graviton as the fundamental gravity carrier and these tensor mesons teaching us about QCD, what are the major theoretical hurdles or implications here?
Well, the biggest one, as pretty much all our sources agree, is finding a consistent theory of quantum gravity. How do gravitons interact quantum mechanically? How do we merge GR and quantum mechanics? That's the holy grail.
And string theory.
String theory is interesting because it naturally spits out a spin-2 particle that looks just like the graviton. That's one of its big selling points. Also, the way massless spin-2 particles interact, governed by the principle of equivalence. That's what leads directly to general relativity on the macroscopic scale. And some theories with extra dimensions predict massive spin-2 particles too, these Kaluza-Klein gravitons.
Extra dimensions.
Okay, that's a whole other deep dive. Let's move down again.
Yes.
Spin-3-halves. Back to fermions.
Correct. Spin-3-halves particles are fermions. So back to Fermi-Dirac statistics and the Pauli exclusion principle.
Okay, and spin states. 4 this time. You got it. 4 possible states. -3/2, -1/2, +1/2, and +3/2.
And the theory for these? The sources mentioned.
The Rarita-Schwinger equation. That's the main relativistic equation for spin-3-halves. It's kind of a mashup, actually.
A mashup.
Yeah, it blends ideas from the Dirac equation, which handles spin-1/2, and the math used for spin-1 vector bosons. The field itself is a vector spinor. It has both vector and spinor parts. Very complex structure.
Sounds like it. So what about real-world examples? Again, fundamental or composite?
Much like Spin-Five-Halves, no confirmed elementary spin-3-halves particles yet.
Okay, seeing a pattern here with the higher half-integer spins.
Definitely. But we have really important composite baryons with spin-3-halves. The classic examples are the delta baryons, delta plus plus, delta plus, etc.
Right, the excited states of protons, neutrons made of up and down quarks.
Exactly, with their quark spins aligned. They're heavier and decay super fast. And then there's the omega minus baryon.
The omega minus, made of 3 strange quarks. That discovery was huge for the quark model, wasn't it?
Absolutely massive. Its discovery, with the predicted spin-3-halves, was a huge win for the quark model and SU3 flavor symmetry. Our sources really emphasize its historical importance. Plus, other baryons with strange charm or bottom quarks can also have spin-3-halves states.
So mostly excited composite particles again. But didn't the reading mention a hypothetical elementary one in this category?
It did, the gravitino.
Gravitino, sounds like.
The supersymmetric partner of the graviton.
Supersymmetry again. Partner particles for everything.
Pretty much. If the spin-2 graviton exists, and if supersymmetry is real, there should be a spin-3-halves gravitino. Its existence is tied to local supersymmetry or supergravity.
And its properties.
Its mass, how it interacts. That all depends on how supersymmetry is broken in our universe. Some models even propose the gravitino as a dark matter candidate.
Spin-3-halves, dark matter.
Wow, that's an idea. So what are the theoretical snags or big questions for spin-3-halves according to the sources? Similar issues to the higher spins, really. Interacting theories with elementary spin-3-halves particles can suffer from acausality or loss of unitarity.
Right. Same problem.
Yeah, you often need specific frameworks like supergravity to make things work consistently. And of course, studying the composite spin-3-halves baryons is still super important for understanding hadron spectroscopy and how quarks combine.
Okay, let's shift to integer spin again, spin 1. Vector bosons, these are the force carriers, right? Hugely important.
Absolutely crucial. Spin 1 particles are bosons, obeying Bose-Einstein statistics.
3 spin states.
Yes. -1, 0, and +1. But, as the sources stress, there's a key difference between massless and massive ones here.
Woo!
Massless spin-1 particles, like the photon, only have 2 actual physical polarization states that transverse, perpendicular to their direction of travel.
Like light waves.
Exactly.
Yeah.
But massive spin-1 particles, like the W and Z bosons of the weak force, have 3 polarization states. The 2 transverse ones, plus a longitudinal one, along the direction of motion.
That longitudinal state that's linked to them having mass.
Precisely. It's a direct consequence of their mass. Seems like a subtle point, but it's very important theoretically.
How are they described? The theories involved.
Well, for the massless photon, you've got Maxwell's equations classically, and quantum electrodynamics, QED, as the quantum theory. It uses a 4-vector potential.
Standard stuff.
Right. For massive ones, it's the Proca equation. And then for the ones like gluons and WZ bosons, which are non-abelian, we use Yang-Mills theory.
Non-abelian, meaning they interact with themselves.
That's the key feature. They carry the charge of the force they mediate. Gluons carry color charge, W bosons carry weak charge. So they interact with each other, not just with matter particles. Makes the theory much richer and more complex.
Self-interacting force carriers. Wild. So their fundamental roles.
Force mediation, pure and simple. Gauge bosons. The photon, gamma, carries electromagnetism, massless, long range. The W plus and W and 0 carry the weak nuclear force, massive, short range. The gluons, G, carry the strong force, binding quarks, effectively massless inside hadrons due to confinement.
The workhorses of the Standard Model.
Definitely. And we also have composite spin-1 particles, vector mesons, quark-antiquark pairs, like the rho, omega, phi's, JP psi mesons.
So what are the big theoretical ideas or maybe challenges linked to spin-1?
Gauge invariance is absolutely fundamental for the massless ones. It's a deep symmetry principle that dictates the interactions and leads to things like charge conservation.
Right.
And the Higgs mechanism is vital for the massive ones. It explains how the W and Z get their mass without wrecking the underlying electroweak gauge symmetry. It's a beautiful piece of theoretical physics detailed in our reading.
Couldn't agree more. The Higgs mechanism is elegant.
So yeah, vector bosons are just central to how the Standard Model describes interactions between matter.
Okay, brings us to spin-1/2. The stuff matter is actually made of, right? The fermions we know and love.
Exactly. Spin-1/2 particles. Fermions. Fermi-Dirac statistics. Pauli exclusion principle. And that principle, as the sources just keep hammering home, is the reason matter has structure.
Atoms, chemistry, the periodic table, all down to Pauli.
Pretty much. It stops all the electrons piling into the lowest energy state. It makes matter take up space. It's fundamental.
And these just have 2 spin states, up and down. Simplest case.
The simplest non-trivial case, yes.
Yeah.
Just 2 states. -1/2 spin down and +1/2 spin up. That binary nature is key.
And the equations governing them, the Dirac equation.
The Dirac equation is the star here. Relativistic, includes spin automatically, predicts antiparticles, gets the magnetic moment right. It's a triumph of theoretical physics. For non-relativistic cases, the Pauli equation works well.
And the example, well, they're everywhere, aren't they?
Absolutely everywhere. All the fundamental matter particles we know are spin-1/2 fermions. You've got the quarks, up, down, charm, strange, top, bottom.
Yeah.
They make up protons and neutrons.
Right.
Then the leptons, the electron, fundamental to atoms and electricity. The heavier muon and tau, and the neutrinos, electron, muon, tau, neutrinos, tiny masses barely interact.
And composite particles, too, like protons themselves.
Yes. Composite baryons made of 3 quarks can also have a total spin of 1/2. The proton up, up, down, and the neutron up, down, down are the most famous. But also lambda, sigma, Xi baryons. Lots of them.
So quarks inside, electrons outside. Spin-1/2 is truly the basis of matter. What are the major theoretical points or remaining puzzles here?
Well, they are the building blocks of visible matter. Their nature as finders, how they transform under space-time rotations, is mathematically unique and crucial. And their interactions via boson exchange is the Standard Model, basically.
But there are still questions.
Oh, absolutely. Big ones. Where do neutrino masses come from? The Standard Model originally had them massless. That's a major puzzle. And are neutrinos their own antiparticles? That's the Dirac versus Majorana question. Still unresolved.
Lots still to figure out, even with the most common particles. Okay, last stop. Spin-0. Scalar bosons. What's special about having no spin at all?
Well, they're bosons, so Bose-Einstein statistics again. But 0 spin means only one state. No intrinsic angular momentum, no preferred direction. They look the same from all angles. Described by scalar fields just a single number at each point in spacetime. Simplest kind of field.
And the equation for them?
The Klein-Gordon equation. That's the basic relativistic equation for spin-zero particles. Foundational for quantum field theory.
And the prime example here has to be?
The Higgs boson. Absolutely.
That's
as far as we know, the only fundamental elementary scalar particle.
The one that gives other particles mass.
Exactly. It's the quantum of the Higgs field, which permeates space. Through the Brout-Englert-Higgs mechanism, interacting with his field gives mass to quarks, electrons, W and Z bosons. The Higgs boson itself gets mass from interacting with its own field, too.
Are there composite spin-zero particles as well?
Yes, scalar mesons. Quark-antiquark pairs with total spin zero, like the S0500, sometimes called the sigma, or the 8R980. Their properties are actually quite messy and hard to nail down because of QCD complexities.
And what about pions? Aren't they spin-zero?
They are spin-zero, yes, but the sources often clarify they're technically pseudoscalar mesons.
Pseudoscalar.
Means they have odd parity. Their description changes sign if you mirror-reflect space. The Higgs is a true scalar even parity. It's a subtle but important difference. And then there's the hypothetical inflaton.
From cosmology, early universe inflation.
That's the one. A proposed scalar field that drove the universe's incredibly rapid expansion just after the Big Bang. Still hypothetical, but a very influential idea.
So, the Higgs, pions, maybe the inflaton. Scalar fields seem pretty crucial, even if they're simple in terms of spin. Theoretical implications. Challenges.
Hugely important. Scalar fields are the key ingredient for spontaneous symmetry breaking. That's how you explain particle masses and hidden symmetries in physics.
Right, the Higgs mechanism again.
Exactly. But there's a big theoretical headache. The Higgs mass itself is very sensitive to quantum corrections. This is the hierarchy problem. Why is the Higgs mass relatively light compared to other scales in physics? It hints there might be new physics we haven't discovered yet.
Like supersymmetry, maybe?
That's one popular idea, yeah.
Yep.
Supersymmetry could help stabilize the Higgs mass. Also, scalar fields are explored in theories of dark energy, trying to explain why the universe's expansion is accelerating now.
Wow, okay, that was quite a tour. From Spin-Five-Halves, which felt pretty exotic, down to the fundamental spin-zero Higgs.
It really covers a huge range, and hopefully what comes through is how particles spin isn't just some abstract number. It fundamentally shapes what it is, how it behaves, and the role it plays.
Yeah, the whole fermion versus boson thing, Pauli exclusion versus Bose-Einstein condensation, it all traces back to spin.
It absolutely does. Shapes matter, shapes forces.
It's incredible, really, this quantum property underpinning so much of reality.
It is. And maybe a final thought for you listening at home. Just consider how this one property, spin, dictates the rules for everything from quarks to cosmos. And then think, what if there are particles with other spin values out there yet undiscovered? What rules would they follow? What secrets about reality might they unlock? Something to chew on.